You guys, this is page 797. No, my gosh, 799. And we're talking about dependent probabilities using the word and. Now, there's a lot of notation here in the first part that is very dense. And so we're going to go through it piece by piece. If event A and event B are dependent, well, there is a basic formula for and means multiply, but there's a certain careful. The probability that event A happens and event B happens is the product of the probability that event A happens. So that's that part of the formula. You're going to have to calculate the probability of event A. The second part is not so nice. The probability that event B happens given that event A already occurred. The key word is given, and it's going to lead us to this vertical line. In fact, specifically, given is how we say the vertical line in between B and A in that notation. The probability of A and B, dependent situation, is the probability of A times the probability of B given A happened, A occurred. It's like in the tree diagram from page 798. What's the probability of getting a blue sock? Well, it depends on what the probability of the first sock is. And then once you're in that branch, the second branch depends on the first one. So of these, we have a different fraction. When you have independent situations, the independent situation says, well, these are equally likely. But once we have dependent, we got to go down the branch into the second row and then figure out the probability from there. Juan is determining the probability that the second sock chosen is red. Analyze his strategy, then use it to calculate the probability. Juan says, we want the second sock to be red, but the first sock can be red or not red. Therefore, the desired outcomes are red and red again, or not red and then red. And if we use that logic with the tree diagram, I'm just going to go ahead and count all of the possible second sock red outcomes. Little star. That's a second sock red. That's a second sock red. That's second, that's second, that's second, that's second, that's second sock red, that's second sock red, and there are the last two. So that means there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outcomes where the second sock is red, but the first sock could be red or not. So I'm just going to write up here in the box 10 out of 5, 10, 15, 20, 25, 30. Remember, it's 30 because go back and look at the video from page 798. There are 30 outcomes when you're not replacing the sock that is drawn out of the drawer. So we have an add now. Add rears its head before the next lesson where we use the word or. Okay? So let's consider this scenario. The first sock is red and the second sock is red. So if the first sock is red, that's 2 out of 6 total combinations. So probability of red times the probability of red given red, which would be 2 out of 6. But then, once you're in the red like branch, then, and both of them have the same thinking, then in the next series of branches, only one of those happens to be red. See, 1 of 5 or 1 of 5. So then the second fraction that's going to be written down over here is 1 of 5. So 2 times 30. Then we go look at the other one. We look at the probability of not red. Remember, the C is the idea of not, so complement, not red. And that would be a different scenario. I'm going to little breaker bar here. This is just kind of separate out. Probability of not red times the probability of not red given, we got that backwards, red, take that out, given not red. So we got to look at how many of our options are not red. And looking at that page, you look at your own, 4 out of 6. And then last of all, maybe I'll slide it back over here. In these not reds, these are red complements. There are 1, 2, 3, 4 of them. In these not red options, for the first one, there are 2 and 2 and 2 and 2. There's 2 of 5, 2 of 5, 2 of 5, 2 of 5. So the second fraction is going to be 2/5. Because in the second branch of the not red initial branches, the second branch divides up into 5 of them, and 2 of those options are 5. So when we multiply fractions, multiply straight across, 2 times 1, 6 times 5, 2 out of 30. 4 times 2, 6 times 5, 8 out of 30. We can add fractions when they have a common denominator, so both of those denominators are 30, which means we can just multiply 2 plus 8, and that makes 10, still 10/30ths. So either way, you could count up, identify and count up in the last row of outcomes of the tree diagram how many of them fit the entire situation, or you could do this lovely, awesome, fandangled sort of like combination calculation. Let's try it again, different scenario. Using Juan's method to answer these questions, what is the probability that the second sock is blue? That is either both socks are blue, or the first sock is not blue and the second sock is. But when we're done, we can be able to count them. Let's go again, tree diagram. Go there first. In the tree diagram, let's count up how many of the last row have blue socks. Last row, yeah. There's one, not there. There's one, and there's one. So 1, 2, 3, 4, only 5 options. So I'm going to right now just say the answer is 5 out of 30 total options. But I want to prove it with the fractions. So the probability that the first sock is blue and the next sock is also blue. Okay, so the probability the first sock is blue is 1 out of 6. But once we're in that blue column, there are no blue socks remaining to choose. Anytime you multiply by 0, the entire calculation is gone. It's just 0. And then we consider the next scenario. So how many combinations of these socks are not blue? Well, there's the 2 reds and the 3 greens. So 5 out of 30. And once you're in the column, 5 out of 30, 5 out of 6 colors. I'm getting to the 30. 5 out of 6 colors in the first row, the first choice, are not blue. And then we're going to multiply by, in the next decision, how many blue socks show up in each of these non-blue starters, but now they're blue for the second sock. It looks like 1 out of 5. And when we multiply the fractions, that's 0, so that's gone. 5 times 1, 6 times 5, it would be 5 out of 30. Of course, you could reduce that to 1/6, but there's really no point to doing that unless you just want to have a simpler fraction for further calculations. When we know we have 5 situations out of 30 total situations, that's the best way to interpret the 5 over 30 and just not even do the reduced fraction. It's frankly not necessary. And it doesn't have the same level of information as this fraction does. There are 5 situations where the second sock is blue. Who cares what the first sock color is? Although you'll never have a blue go first because once you do, you don't have a second sock blue. What's the probability the second sock is green? Let's build the notation. So the probability that the second sock is green, well, the first sock has to be green and the second sock has to be green. And we can add to that the probability that the first sock is not green and the second sock is still green. So that would be the probability of green sock for the first choice times probability that your first choice was a green sock. So that's why there's a green here. In fact, that green is meant to be that green. And then the second sock, this is sock number 2. Your second choice is green. We're going to add to that the probability that your first, no, this is now second sock. So your second sock is green given the probability the next sock is green, but the first sock wasn't. This needs to be a complement right there. Okay, so I'm not looking at the tree diagram yet. I want to do this in reverse of those last 2 questions just to check that I'm on the right track. So probability of a green sock is 3 out of 6. And then the probability that the second sock is green is 2 out of 5. Because once you've drawn a green sock, there's only 1 left, but you've already taken your 6 options and whittled them away down to 1, so 2/5. And we're timesing, and we're adding. Now, the probability of getting not a green sock is still 3 out of 6, but you didn't take away a green sock. You still have 3 remaining. So there are 3 socks remaining out of 5 options in the second row. We still have 6 times 5 and 6 times 5, so the final answer is going to be out of 30, but we need to do the multiplication of the top numbers. 3 times 2 plus 3 times 3. Okay, apparently, I'm going to go back to the tree diagram and I'm going to find 15 situations where that's happening. I might as well use yellow. I'll use yellow because on my tree diagram on the other page, there's no yellow. I'm looking for second sock green. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. End of the tree branch diagram, highlighted them. The second sock is green. There are 15 total of them, and that's what I confirmed right there. 15 out of 30. What questions to consider do I have for you? Do you recognize what each product is supposed to represent? Like, you got to be thinking about where those numbers came from. I hope I've been clear that in all of the fractions, they can get confusing and lost. But if you built a solid quality tree diagram, you can use this to answer all of our probabilities just by counting up your options out of the total number of options. So the product of the fractions is important, but build a good tree diagram. Another question, verify your calculations using the sample space. You know what I did? I did verify the calculation 15/30ths because when I was done calculating, I went back and counted. You should really do that. This has been a long video, but there's been a lot of math in here. The next video is really the wrap-up for Lesson 2. It's about talking about what we discovered. So please pay attention. Stick forward for that one. Thank you for watching this video. Like, comment, and subscribe. I'll see you in the next episode. Page 800 is next.